We're going to talk now about molecular geometry, which has to do with three-dimensional shapes of different molecules. So the underlying theory for molecular geometry, or what the shape of a molecule is going to be, is something called Vesper. Okay, so Vesper is actually an acronym for valence, shell, electron, pair, repulsion. That's a lot to say. That's why we just call it Vesper for short. Okay, but the basic idea behind Vesper is that we can predict what the shapes of molecules are going to be based solely on how many pairs of electrons there are. And for now, we're going to count bonded and non-bonded or lone pairs the same, even though they do have slightly different shapes. Okay. The underlying theory behind Vesper is really that all of these pairs of electrons are going to orient themselves in 3D space in such a way to kind of minimize different kinds of unfavorable interactions and maximize all of the favorable interactions. Okay, and so you say, well, what's good and what's bad, right? What's favorable and what's unfavorable, okay? We're going to just focus on two things, okay? One of them is called an electrostatic interaction, which basically is a nice way of saying charges, okay? And so things that are negatively charged are going to repel each other, but one thing that's negative, one thing that's positive will attract each other. So the point is that all of these electrons, because they're negatively charged, want to be as far away from each other as possible to try to maximize the distance between them. The other thing that matters, right, number two, is steric hindrance. Steric hindrance basically says that things that are really big and bulky need their space. Okay, and so they're going to try to get as far away from each other as possible if you have two relatively large objects or pieces of large objects, so that they have enough room to move around. Okay, so at the heart of Vesper is something called an electron group. And so an electron group is any collection of valence electrons on a central atom that's going to affect the overall structure of the molecule. So this electron group could be one single electron by itself, which is called a radical, or it can be a pair of electrons, non-bonded electrons, which would be called a lone pair, or it can be a pair of electrons that are covalently bonded, which is a single bond, or it can be two pairs of electrons that are covalently bonded, which we call a double bond, or it can be even three pairs of electrons that are covalently bonded, which we call a triple bond. Okay, and so what I'm going to do now is show you what this might look like in tabular form, so you can summarize all of the different shapes of these different molecules based on the numbers of electron groups. Here are the different electron group geometries, and they're based for now solely on the number of pairs of electrons. Okay, and so if I only have two electron groups, okay, this basically means that I only have two pairs of electrons. Okay, and so let's pretend that my torso here is the atom in the middle, which we're going to call the central atom, and over here is one pair of electrons, and over here is another pair of electrons. Okay, my arms represent the bonds between these atoms. Okay, the point is that these electrons here and these electrons here repel each other, so they want to be as far away from each other as possible. And so the best way to do that, if I move my arms around, is right about here, okay, 180 degrees apart. So that's going to be a linear geometry. So imagine a central atom here, and then one here, and another one over there. Okay. If I have three things in space, and I want to keep them as far away from each other as possible, the best way to do that is what's called a trigonoplanar geometry. So one in the middle, and then the other ones are going to be about 120 degrees apart, as opposed to 180 for the linear geometry. Okay, four things in space happens to be the most popular situation because four things in space is probably four pairs of electrons. Four pairs is really 8 electrons, which is the octet rule. So we're going to have one thing in the middle, and it turns out I can't really do it in 2D, but I can do it in 3D. Okay, basically I want to have a pyramid, and the angles here are all 109.5 degrees. If I have 5 things in space, this is called the trigonal bipyramidal structure. So I'm going to have one here, one here, one here, and these are all in the same plane. And then I have one above the plane and one below the plane. Or I can have what's called an octahedral geometry, where everybody is 90 degrees apart. And so I have basically two atoms in the x-axis, two atoms along the y-axis, and two atoms along the z-axis. These angles that I'm giving you of 90 or 90 here, or 120 here, or a 9.5 here, or 120 there, or 180 there, these are all ideal. Okay, they're going to actually change a little bit depending on the structure, which has to do with what's called molecular geometry. So the idea behind molecular geometry is to try to distinguish between bonded and non-bonded electrons. So before, we assumed that all of the electron pairs were exactly the same, or all the electron groups were the same. But it turns out that lone pairs actually make a little bit of a difference. Okay? And the reason that they make the largest difference is because the lone pair, in a sense, only belongs to one atom instead of being shared by two nuclei. So the electrons are only really attracted to one center instead of two. That allows them to be spread out a little bit more and exert a greater repulsion between the electrons. Okay, and so it turns out that the repulsions between the lone pairs are very strong compared to the repulsions between bonded pairs and lone pairs, or between bonded pairs and other bonded pairs. So when we're using Vesper theory to describe shapes of molecules, there's a certain designation that we have to follow. Okay, to show you the table in a minute, I want to make sure you understand how to read the table. Okay, and so the designation is AXNEM. Okay, and so the A is the symbol for the atom in the middle, the central atom. The X's represent all of the atoms on the outside that are bonded to the central atom. So these have bonded electron pairs. And the E's represent lone pairs, or non-bonded electrons. Now the subscripts, the N and the M, refer to how many of these things we have. Okay, and so N can be any integer between 2 and 6. It could be 2 or 3 or 4 or 5 or 6. And M is also an integer between 0 and 3. Okay, so 0, 1, 2, 3. So what I'll do now is show you a table depicting all of the different molecular geometries for all the different shapes that you're going to come across in chemistry. So let's start out with two electron groups. This is going to have a linear geometry like I showed you before. The Vesper notation is AX2, and the angles here are going to be about 180 degrees. And an example would be something like beryllium chloride. But by the time I get to three electron groups, there's actually two possibilities. I might have three bonded pairs and no lone pairs, in which case it's the trigonoplanar one that I showed you a minute ago, or I could have two bonded pairs and one lone pair, which I call AX2E. And so the point is that this is now angular or bent. So the angle changes slightly, right? Instead of 120 degrees, it's about 118 degrees. This difference of 2 degrees or so is due to this extra lone pair repulsion that we mentioned earlier. Now, when I get to 4, this is the most common situation, like I mentioned before, because 4 electron groups might represent 8 electrons. These are all in the tetrahedral family, but I have 3 different possibilities. I could have all 4 bonded pairs, or I could have 3 bonded pairs and 1 lone pair, or I could have 2 bonded pairs and 2 lone pairs, which gives me slightly different molecular geometries, even though they have exactly the same electron geometries, right? They're all tetrahedral, but I call them different things depending on these slightly different variations. For example, 3 bonded pairs and 1 lone pair shifts the angle from 109.5 to 107, so another 2 degrees or so. And this is called trigonal pyramidal. If I have 2 bonded pairs and 2 lone pairs, now the angle changes even more to about 105 degrees. This is also called angular or bent. It's a bit unfortunate that they're both called angular bent here, but you can tell which one is which by the angles, right? They're very different, 118 versus 105, and or by the context, right? How many pairs of electrons you have total. Okay, now let's move on to things that have more than 8 electrons, which are sometimes called expanded octets. Okay, so if you have 5 electron groups, these are all in the trigonal bipyramidal family. You can have 5 bonded pairs and no lone pairs, or you can have 4 bonded pairs and 1 lone pair, or 3 bonded pairs and 2 lone pairs, or 2 bonded pairs and 3 lone pairs. And again, the shapes are almost exactly the same, but they're a little different. So if they're all bonded, I call it trigonal bipyramidal, just like the name of the electron group. But if I only have 4 bonded pairs and 1 lone pair, I call this a seesaw shape. If I have 3 bonded pairs and 2 lone pairs, I call this T-shaped because it looks like the letter T. So all these angles are 90, and then this angle here is 180. Or if I have 2 bonded pairs and 3 lone pairs, it actually goes back to linear. Okay, so now the 2 things that are bonded are 180 apart from each other. And the last possibility is if I have 6 pairs of electrons, which are all in the octahedral family. So if I have all 6 bonded, all the angles are either 90 or 180. But if I have 5 bonded pairs and 1 lone pair, I call this square pyramidal. And if I have 4 bonded pairs and 2 lone pairs, I call this square planar. Okay, and so this series of colorful tables was meant to show you all of the different shapes that are possible for different molecules. And what you have to do is figure out, based on the number of pairs of electrons, and furthermore, what kinds of pairs of electrons they are, whether they're bonded pairs or non-bonded pairs, what the molecular geometry is going to be for these different compounds. Let's talk a little bit about isomers. Okay, and so isomers are things that have some things that are the same, but then some things that are different. Okay, there are different types of isomers. Okay, so for example, structural isomers have exactly the same chemical formula, but they're connected differently. Okay, one example would be in coordination chemistry or complex ions, the donor atoms that are on a ligand. Okay, and so for example, something called pentamino nitrito N cobalt 3 versus pentamino nitrito O cobalt 3. Okay, and so the atoms that are highlighted here in red are the atoms that are actually forming this coordinate covalent bond between the ligand and the central atom, or in this case, the central metal ion. Okay, and so in the first case, the nitrogen of the nitrito group is forming some kind of coordinate covalent bond to the cobalt, whereas in the second example, one of the oxygens for the nitrito group is forming that coordinate covalent bond to the cobalt ion. Or another example would be if something is a ligand, meaning very close to the central atom or central ion, versus something that's a free ion and like outside of the coordination sphere. Okay, so for example, the first one is pentamine sulfato-chromium 3 chloride. So here, the sulfates and the amino group, or the ammonia, NH3, those are all considered inside, or ligands, but the chloride is outside, right, not part of this complex ion, versus the second one, pentamine chlorochromium sulfate. Now the chlorine and the amine, or the ammonia, are inside, right, those are all ligands, and now the sulfate is on the outside. Another type of isomer is something called a stereoisomer. Okay, and so stereoisomers have the same atoms that are connected in the same way, but they have different 3D shapes. Okay, in 3D space, they look a little different. So you can have geometric isomers, or you can have optical isomers. So geometric isomers have the same groups that can be on the same side of each other or on opposite sides of each other. If they're on the same side of each other, it's called cis, CIS. If they're on opposite sides, they're called trans. Okay. Optical isomers are mirror images of each other that are not superimposable. Another word for this is enantiomers. Okay, and so think of your hands. Okay, these are mirror images or enantiomers of each other. Okay, they're not superimposable. There's no way that I can take my right hand and superimpose it on my left hand. Okay, I can't do anything. I can do this, but they're not the same, because even though the fingers seem to match up, this one has my palm up and this one has my palm down. And if I turn so that they both of my palms are up, now my thumbs are on opposite sides. Okay, so this doesn't work. Another word for this is chirality. It turns out that optical isomers are all called chiral molecules. Okay, they have identical chemical and physical properties, except for one, which is how they rotate polarized light in a polarimeter. Okay, another word that you might be familiar with is something called a racemic mixture. a racemic mixture happens to have exactly equal amounts of these two mirror images, or these two enantiomers.